Hey, Algebra 1. Yesterday we did the power of exponential growth. Today we're going to talk a little bit more about exponential growth. So to start out, we've got two graphs here. We're going to compare the two graphs and make conjectures. Remember, conjectures are guesses about the rates of change. As we talk about the conjectures, we're going to talk about accuracy, and we may have to investigate a bit closer. So Callie and Joe are examining the population data in the graphs below for a history report. Their comments are as follows. Callie, it looks like the U.S. population grew at the same amount as the world population, but that can't be right, can it? Joe, well, I don't think they grew by the same amount, but they sure grew at about the same rate. Look at the slopes. Remember, rate is our slope. So rate is the same as slope, which we do change in y over change in x, which is rise over run. But let's talk about this. So I've got the world population. Joe's saying it's the same slope. Callie is talking that they grew the same amount. Well, I've got population in millions. We went from about 22,500, actually, this is in millions, so 1, 2, 3, 4, 5, 6. 250 billion is the population where it starts. And so this is in millions. We're just going to talk millions. So 2,500 in millions up to 6,000 between 1950 and 2000. Here we're at, it's not the same amount because we're at 150 in millions all the way up to about 275 in millions between 1950 and 2000. So, no, Callie is not correct because it wasn't the same amount. When you look at a graph, you actually have to look at the XY axis and the units, everything. So the world population grew by far greater. Is Joe's observation correct? No, Joe ignored the scale. It looked like the same slope, but he ignored the scale, just like Callie ignored the scale. So the rate of change, or the slope, the rate of change or the slope is much greater for the world population than the U.S. population. So let's use the world population graph to estimate the percent increase in world population from 1950 to 2000. When we do percent increase, we do the difference in the two values over sort of over the start. I'm not explaining that well, but let's use some math. So in 1950, we're going to use 2,500 million, and then in year 2000, we're going to use 6,000 million. Yes, million. So if I do the year 2000 minus 2,500, so that's my difference, over 2,500, I get 140%. I have to change that decimal into a percent. Now use the U.S. population graph to estimate the percent increase for the U.S. population. So in year 1950, we're going to use 150 million, and in year 2000, we're going to use 280 million. So the difference divided by the start. So 280 minus 150 divided by 150 times 100. 0.866 times 100 gives me 86.7% if you round correctly. So how does the percent increase for the world population compare to that for the U.S. population over the same period? The U.S. population was increasing faster. Oh, no. Sorry, I said that backwards. I could just erase or rewind the tape, or the recording, so the world population was increasing faster because it was a bigger percent. Because that was 40%, and this was 87%. Yep. Do the graphs above seem to indicate linear or exponential population growth? Just looking at the graphs, so visually, no. For that time frame, it appears linear. The world population, if you look at the graph, appears to be increasing about 70 million per year. And then the U.S. population looks to be increasing about 2.6 million per year. If you just do the slopes. To calculate this, I just went 6,000 minus 2,500 over 50 years. So let's do that. Over the year 2000 minus 1950, so that's 50 years. That's about 70. And then for the U.S., let's see, I was at 280 minus 150 over the year 2000 minus the year 1950, which is 50 years. That gives me about 2.6. So the world population is growing at a faster rate than the U.S. population. So write an explicit formula for the sequence that models the world population growth from 1950 to 2000 based on the information in the graph. Assume the population in millions in 1950 was 2,500, and year 2000 was 6,000. So we know our increase each year was, so from year to year, we just calculated that our population increased by 70 million each year. So that is how we're going to write our explicit function. You guys got really good at that over the last few lessons. So 70 times t, and then our beginning was 2,500. So we're starting with 2,500, and we're increasing by 70 each time. It's a linear equation, right? This is what we see, y equals mx plus b, where that is our m, and that is our b. We're going to start with, we always do time, is greater than or equal to something. We started in year 1950, so we're just going to leave this off for now. Sorry. Okay, so our explicit function, it's getting a lot easier, I hope. All right, let's look at another one. How is this graph similar to the world population graph in mathematical modeling exercise 1? How is it different? So we have world population again. Our years look to be extended a little bit. I'm at year 1700 to year 2000, and my population is itty-bitty-ish all the way to 6,000. So we're still at 6,000, but we've extended down to the beginning. This looks to be exponential, where the last one looks to be linear. So this graph uses the same vertical scale, but the horizontal scale is different. So this has been extended. The horizontal scale has been extended. The graph itself shows it looks to be exponential. Does the behavior of the graph from 1950 to 2000 match that shown on the first exercise? Yeah, they're both linear at that point, so yes. In 1950, it shows 2,500, and in year 2000, it shows 6,000 million. So that is the same. Why is the graph from exercise 1 somewhat misleading? It appears as if the world population has grown in a linear fashion when it has really grown exponentially. An exponential formula that can be used to model the world population is as follows, where 2,519 represents the world population in 1950, and T represents the number of years after 1950. Use this equation to calculate the world population in 1950, 1980, and 2000. How do your calculations compare? So if I look at 1950, that'd be T equals 0, f of 0, so 1950 T equals 0. I have 2,519, to the 0. So my answer, this actually becomes 1, calculates to 1, so that is my answer. And 1980, I have T equals 30. So 1.0177 to the 30th. Calculate that out and I get 4,264 million. And then in year 2000, it's f of 0 to the 50. That gives me 6,056. That's pretty close if you compare that to the graph. I'm pretty happy with those calculations. So the following table shows the world population numbers used to create the graph above. How do the numbers in the table compare to those you calculated in part D above? 2000, 1950, and what else did we calculate? This one. If I look at my calculation for 1980, I had, 4,264, and this one, 6,056. Pretty darn good, right? I think they're all reasonably close. And then the last one, how is the formula in part D above different from the formula in exercise 1? This is that formula. Well, this one is linear, and that one is exponential. Which formula most closely represents it? The exponential one, because when we expanded the x-axis, our exponential model was much clearer than the linear model. So the exponential model is the correct one. The table below represents the population of United States in millions for the specified years. I have 1800, 1900, and 2000 just for the U.S. population. If we use the data from 1800 to 2000 to create an exponential equation representing the population, we generate the following formula where f of t is the U.S. population and t represents the number of years after 1800. So we're going to check 1900. So that would be f at 1,000. Oh, it's for 2010. Sorry, I did not read the entire problem. So year 2010 would be, we're going 210 years after 1800. So we would have 5 times 1.0204 to the 210. That would give me a population of 347 million in 2010. If we use the data from 1900 to 2000 to create the exponential equation that models population, we generate the following formula to the sequence, where f of t represents the U.S. population and t represents the number of years after 1900. Use this formula to figure out the population in 2010. So after 1900, that's 110 years. That gives us 76 times 1.013 to the 110. Calculate that out, and that has 315 million in year 2010. I spelled that, or I got that wrong. Hold on. 2010. So the actual U.S. population in the year 2010 was 309 million, and we just calculated 315 million. Which of the above formulas better models the U.S. population? The last model we calculated 347 million. Which one is closer to 309? I'd say the second model. The one in part B is a closer approximation. Although the population of the U.S. is still increasing exponentially, the rate slowed considerably in the past few decades. So to include 1800 to 2010 is giving us a good guesstimate of the current population. Pretty cool. So let's complete the table below to show the projected population. We're using the formula from part B. So we're at years past 1900. So this would be 120, 130. Sorry, that's a 50. That's really funny. 150 and 180. We're going to use it in the equation f of t. 76 times 1.013 to the 120, f of 150, 76, 1.013 to the 150, and finally 76 times 1.013 to the 180. That gives me 358 million, 528 million, and 777 million. Okay, those are the projected populations as years go on. Yikes. Are the population figures you computed reasonable? What other factors need to be considered when projecting population? Reasonable, that's sort of a opinion. It doesn't take out, like the numbers don't take into account any changes in technology. You know, we can keep the elderly alive longer with health care. Both of those will keep the elderly alive longer. And reduce birth rates or increase birth rates. Food supply. There's lots of things we could talk about. All right, last one. The population of the country of Oz was 600,000 in the year 2010. The population is expected to grow by a factor of 5% annually. The annual food supply of Oz is currently sufficient for a population of 700,000 people, and is increasing at a rate that will supply food for an additional 10,000 people per year. Whew, that's a lot of stuff. So write a formula to model the population of Oz. Is your formula linear or exponential? We're going to go with exponential because population exponential makes better sense. So population in time, our initial value is 600,000. and we're increasing by 5%. So we're really using that future value equals present value 1 plus rate to the time that we learned when we talked about banks and money. And you need to know that equation, so you can use it. So that would be the exponential formula for population. Now the formula for food, that one's linear because we are adding 10,000 per year. The food supply will support 10,000 people per year. So that one is going to be linear. So food as a function of time, I know I can support 700,000 people, and I can support 10,000 more each year. Okay? Equations are not easy to come up with, but I know you guys can do it because we keep practicing them. So at what point does the population exceed the food supply? I would put both of these into my calculator. Y1 with one equation, Y2 with the other equation, and look at it. So this one's my exponential population. And I'm going to start in the year, where are we at? 2010. We're going to make that year 0. And this one's going to be my linear function. Also going to start that in 2010, which I'm going to make year 0. And when I plug those both in, I'm going to check my table. I'm going to see that in year 2015, which for 2010 is 0, 11, 12, 13, 14, 15, year 5. So in 2015, the population exceeds the food. If Oz doubled its current food supply to 1.4 million, would the shortages still take place? Yes, so it doubled its current to 1.4, so that means our linear equation would be 1.4 plus 10,000 t. Put it back into the table. Y1 is staying the same. Change our Y2 to the new equation. We're starting in 2010, which is year 0. When I look at my table, I see that in year 21, which 2010 plus 21 equals 2031, haha. The food runs out. Okay, practice that, please. I'm begging you to pull out your calculator and practice that. To use those tables, they're really pretty awesome to use. So if Oz doubles both its beginning food supply and doubles the rate at which the food supply increases, would the food shortages still take place? So our population equation does not change, but doubling the beginning food supply is now 1.4 million. So we went from 700,000 to 1,400,000, and then doubling the rate which the food supply increases from 10,000 to 20,000. Y1 I'm going to keep the same. I'm going to put in my new equation for Y2. And I'm going to see from year 0, which is 2010, all the way to year, look at my calculator, looks like 24, which is 2034. They run out of food. That's sort of scary, isn't it? All right, that's it. Practice those equations, and we'll do them again in class. Please make sure you ask if you're not sure what's going on. I would love to help.